Measurement uncertainties. We continue, yeah, to study this one. This is the first chapter of physics, yeah. Measurement in physics. In physics, measurement is the process of assigning a numerical value and a unit to a physical quantity by comparing it to a standard unit. It quantifies properties of objects, even enabling scientists to record, analyze, and compare observations. The key components of measurement include the physical quantity itself, length, mass, numerical value, how many units, and the unit, of course, we have to use the international standard unit in the metric system, meter and kilogram. First, the scientific notations. In physics, scientific notation is used to write extremely large or small numbers in the standardized and compact format by expressing them as a coefficient between 110 multiplied by a power of 10. This is the example. We have 452 million, yeah, and we have to write it down. So the number of zero in here is too much. That's why in physics we want to make it a very simple. We make it simplify, become 4.52 multiplied by 10 power by 8. Okay, and now is 0.0056. We simplify this number, become 5.6 times 10 power by minus 4. We always use the power of 10. That's a scientific notation. Okay. And prefix. Prefix is a symbol placed before a unit of measurement to denote a multiple or submultiple of the unit, allowing scientists to express very large and very small quantities conveniently. We are using tera, giga, mega, kilo, deci, centi, milli, micro, nano, and pico. Tera, giga, mega, kilo is the large numbers, and deci, centi, milli, micro, nano, and pico is a very, very small number, yeah. This is what we call it prefix. We also symbol, we using capital mostly for the large number, like tera, giga, and mega. We use a capital, yeah, capital font, and small fonts for the small value. Example, we have 520 gigahertz. We find the giga in here, so we multiply with this one, 10 power by 9. We have to make it in standard form. It's become 5.2 multiply with 10 power by 11 hertz. Yeah, of course we have to make it in standard form. We continue again. 452 nanometer. We find which the nanometer is. This one is nanometer, right? 10 power by negative 9. We make it into the standard form, become 4.52 multiplied by 10 negative 7 meter. I think it's easy, yeah, prefix. We're moving forward then. And this is a significant figures. There's a 3 number here. We have to find how many significant figures in here. Okay. This one is 3 significant figures. Okay, next, the second number. We have 5 significant figures. And the third number, we have 4 significant figures. Okay. And now is a multiplication of the significant figure 2.1 and 2.12 multiplied with 5.778. This is a 3 significant figures, and this is a 4 significant figures. We multiply, yeah. The result in here we have to approximately have to become 3 significant figures. So the result is have to be 12.2. Okay. That's a significant figures. Now measurement and errors, we have to write down like this. X is the measurement value, and delta X, we name it measurement error or uncertainties value. If we read this one, this is the measurement value, and the mistake we made is the uncertainties value or measurement error. Yeah, we are humans, of course we still have errors to have any kind of measurement that we use, yeah. Now we are in a single measurement. Single measurement are very fast, but highly susceptible to the random and systematic errors. Okay, continue again. This is single measurement. The example we're using a vernier caliper. Okay, before we start this, yeah, we discuss this problem. I think you can try to answer the question first. Okay, if you already answered the questions, you see how you read the vernier caliper correctly. Starting with the 0, of course, with 3.6 centimeter, and you start to find which upper and lower jaw meet together. Preferring here. Okay, then we have the X. X is 3.665 centimeter. Because we're using in a single measurement, we realize single measurements have the uncertainties value is half of the smaller scale of this vernier caliper. So we have the uncertainties, we multiply with 0.5, yeah, with the smaller scale, and we got this answer. Yeah, this is how we find single measurements. This is the vernier caliper. Okay, we're moving forward. Single measurement again, but now we're using micrometer screw gauge. Okay, I give you time to try to answer this question first. You can pause this video. Okay, we discuss, yeah. Look at this one. Absolutely, this 7.5 millimeter. Okay, now the rows that we found in here and here is meeting in here. So this one is must be 0.18 millimeter. And X we got is 7.68 millimeter. And remember, we're using a single measurement. Single measurement will use half of the smaller scale. This is the result that we have with micrometer screw gauge. Now we talk about accurate and precise. In my class, we already discussed what is accurate and what is precise. Accurate measure how close a measurement to the value or the two accepted value, while precision refers to consistently repeated measurement. So how consistent that you made, that's what we call it precision, yeah, precise. Multiple data, an experiment of measuring the length of 2.12 centimeter object. This is the first experiment, 2.13, the second experiment, 2.12, and the third, 2.11. Okay, we made the average. I think average is easier. You just add all of them and divide the number of the experiment. The number of experiments we made in here is 3 times, so you divide by 3. This is the average length we got. And of course, we want to find the errors, right? We put the 2.13 minus 2.12, and we got 0.01. 2.12 minus 2.12 is 0. 2.11 minus 2.12, and remember this is an absolute value, so we have to find the positive value. The result is 0.01. So we average this number, we got this 0.007 centimeter. Okay, This is the value, yeah. That's our experiment result. Don't forget to write that this is the value of the measurement, and this is the errors that we have here, the uncertainties value. We make it percentage, we got 0.3%. And this is how we define this is accurate or not. We reverse from the accepted value or true value, and we got this value. This is what we call it accurate, and we got this value is really consistent, yeah, less than 1%, as we call it, with very precise. This is accurate and also precise. Okay, uncertainties. This is the formula of uncertainties. You can try to memorize or you can write it down the formula. You already follow my class, I think you already accept this formula in my class, right? Yeah, you can screenshot or whatever you like. Okay, we continue with the example value. We have a cylindrical cylinder. Yeah, we have the radius. The radius is 5 centimeter with the asymptotes of the radius is 0.025 centimeter. And also we measure the height of cylinder stand, and the uncertainties is 0.05 centimeter. So we have to calculate the value and uncertainties of the volume. Yeah, usually we answer in percentage, but it's okay if you answer in the decimal, still okay. Okay, look at the formula of the volume. Is pi r squared multiplied by the height. Of course, we don't use the pi. Pi is just a constant number, yeah. This is the formula of this. Remember, the radius is square, yeah. Yeah, the 2 is become a multiplication number in front of the uncertainties of the radius. Okay, we just put the number then you get the answer. This is the uncertainties of the volume. Okay, that's the review of the first chapter of measurement and uncertainties in physics. I hope you can learn this or more and have a good result. Thank you for your attention. Thanks for watching. I hope you enjoy learning with me. Don't forget to like, share, and subscribe so don't miss. Please email me or WhatsApp my number if you have any questions. Thank you so much. Bye.